Okay, so if you have constant acceleration, that's equivalent to any one of these equations, because all these equations are equivalent. If you have this equation, you integrate and you get this one. You integrate again and you get this one. And where v of 0 and x of 0 are just integration constants. But they tell you what the position and velocity are at the beginning instant. Okay? If you have just this equation, well, this one follows by taking a derivative, this one follows by taking another derivative. So all these equations, all three of these equations are equivalent. So any one of them is equivalent to constant acceleration, because of course that's what this is anyway. Okay? Now, I've got accelerations F net over m, and I better also say this is constant. Because if I don't say that, it's not true anymore, because you have an F net over m for a pendulum, and these equations sure don't apply to a pendulum. Okay? Now, one reason I started with a pendulum is, again, to get the mathematics out of the way and to make the point of how pictures and graphs and mathematical analysis and experiment all work together. And we'll do some experiments on Friday, yeah. This, incidentally, is a simple harmonic motion, and I think I mentioned that before. So, you just put rotating beam, goes around to a point, then it comes back, and rotates and comes back. Okay? You're losing energy in that thing because of friction, so it's not perfect simple harmonic motion. It's damped simple harmonic motion. And that can be analyzed. My differential equations class is in the process of analyzing damped motion. Until you take differential equations. I'm not going to lay differential equations on you. Okay. I could teach you how to do that in one session, but it's beyond the scope of the course. So unless you get bored and really want more, maybe it's too early for that. I'm sure you'll be totally bored. You know, probably have the whole course done by middle October, right? You guys are good. You're not that ambitious, I don't think. You got other things. You got lives. You got a job. You know. Okay, so we'll do well to get through the course without embellishing. Okay, so we have SI units. Okay, that's standard international units. Okay. Undefined quantities are mass, length, and time. For mechanics, that's all you have. There are other undefined quantities. So I'll just put in parentheses like amps, okay, and candela, and stuff that we'll talk about a little bit second semester, okay? Like candle power. There's your light energy, or light intensity. Okay, well, anyhow. These three are the ones that we're going to be dealing with in this course. Okay? Now you do have temperature, kelvins, but don't have room to write it. And we might deal a little with that this semester. Okay, so mass is in kilograms. Length is in meters. Time is in seconds. Okay? And you know, to be consistent, since I wrote down amps and candela, those are units. Okay, amps measure current, electrical current, and you know, have heat currents also, so say electrical. And candela measures something I don't want to mention right now. It's a little more complicated. Involves these units as well as others. Okay, so anyhow, so there we have it. Well, we have derived quantities. Okay. Velocity, which is rate of change of position with respect to time. Okay. Well, change in position has units of length and time has units of seconds, so that's meters per second. Acceleration. It's the rate of change of velocity with respect to time, which is meters per second divided by seconds, which is meters per second squared. And another one that's kind of interesting is jerk. Know what jerk is? It's the rate of change of acceleration with respect to time. Okay? If you're in a car that's accelerating and the acceleration suddenly changes, you get jerk. Because of Newton's second law, or Newton's second law allows you to at least think about that. So that's kind of in parentheses, not a totally important quantity, but for intuition, it's a good thing to think about. Okay, so you have these derived quantities, okay? You have force, and that's the one I'm wanting to get to so that we can do something here, okay? Well, net force is mass times acceleration. So what's the unit of force?
Kilograms. Kilogram meters per second squared.
Yeah. Unit of mass is a kilogram. Unit of acceleration is a meter per second squared. So unit of force had better be a kilogram times a meter per second squared. Now that's what we mean by a Newton. Okay? So obviously, well, if net force is mass times acceleration, then F net over m had better be acceleration, right? So where we've got F net over m up here, we could write acceleration, couldn't we? I wanted to write it this way first to relate it to Newton's second law, just to emphasize the importance of it and now the understanding the units of it. Okay? Okay, so this can be written, F net over m is A, you got the 2 in the denominator, so F net over 2m is 1/2 A. So we have this. V I'm do something else here. I'm going to put a T in here. And now I'll say A of T is F naught over M. But for constant acceleration, clearly that's constant, so we just designate it by A. So sometimes A stands for just plain old constant A, sometimes it stands for an acceleration function. It's a function of T, as in simple harmonic motion. You can tell from context. That shouldn't cause you a lot of confusion, but just in case I wanted to mention it, okay? So we have these three equations. And these three equations are sufficient to analyze any uniformly accelerated motion. Okay? Now, looking at the time, trying to see how much I have time to do. Yeah, I'm starting to make a statement that I really need to do some background, so I'm going to try to do it. Then I'll give you some problems and see if you can do a few simple problems for Friday. Then give you some complicated ones for Monday and Wednesday. Okay? Okay, so. Okay, this formulation does it. It's a little more convenient, and you can prove from this formulation that it's true, that for any interval of uniformly accelerated motion, we have the following. Time interval delta t. A displacement delta x. An initial velocity that I'll designate v sub I. A final velocity that I'll designate by v sub f. An acceleration a. A change in velocity, which I'll call delta v. Then I thought I already, yeah, I did. There's another one I'm not thinking of right now, but I'll just write these down. Oh yeah. Started to write the first one down. I said, well, there's average velocity. I didn't write that one down. Okay. any three okay, yellow underline on those, and yellow underline here. Okay? Any three of these are known. All others can be found. Delta V and V bar are necessary to completely understand the relationships. And John, you're getting back there. If you got to go, you can, because we'll start with, I'm just going to write down some equations that you see in your book. Yeah. Have you ordered the text?
Textbook now.
Huh?
Do what?
Yeah, you need to order the text.
Where is that?
Check the website. It has all the information, which edition.
Okay.
Okay? And it's still a little time to get it, you know. Have it within a couple of weeks will be okay, because there's another text I can make copies of legally. We can use it temporarily.
A textbook full of problems
It's a
that we'll work
12th
on.
edition. It costs about a quarter of what the full edition costs. And we don't need all the bells and whistles of the new edition. Great text. Okay?
All right.
Okay, good.
Thank you.
Okay, just to complete this, you can check the video if you want, but yeah, it's just 4 equations. You'll have no trouble with them.
All right.
Okay?
See ya.
So, okay, this says that your displacement is the average of your initial and final velocity times the time interval. Okay? Just the average velocity times time interval.
Which one doesn't it V sub I instead of V sub 0?
Yeah, I'm used to writing it with the 0, but since I'm using V sub 0 in the other equation sometimes. So, and I think your text uses V sub I. Okay, this one, which just says you multiply your acceleration by delta t, it tells you how much the velocity changes, and it's equivalent to just the definition of acceleration is the rate of change of velocity with respect to time. In a way, it's fairly obvious. Okay. Okay, this is equivalent and it should be delta x. Equivalent to that equation that we got, that's simple integration. And this. Derivable from the first two equations by eliminating delta t. Treat these as simultaneous equations. Solve one for delta t, plug that into the other, you get this. And I'd use V naught again. I'll probably do that a lot, so watch me. Okay? So you got these equations. If you know any three of these,
Find the rest of them.
they will fit one of these equations, giving you another one, and then you know four of them, and you can use any equation that has the one you don't know to find it, okay? So that's very convenient and handy for the limited case of uniformly accelerated motion, which however is going to be pretty important. Okay?